So one end of a light inextensible string is attached to a particle A of mass m. The other end attached to a second particle B of mass lambda m, where lambda is a constant. It's a rough plane. The string passes over a smooth pulley, and it is all hanging as you might expect it to be. The coefficient of friction between A and the plane is mu. They've not given us much to go on here, have they? It is given that A is on the point of moving down the plane. Find the exact value of mu when lambda equals a quarter. Right, we need some diagrams. We've got two particles, so we need to treat the two particles separately. That's what we do. So particle A, here is particle A. That's the one that's on the plane. So let's put some forces in here. It has a tension in the string. It has a mass of m, so it has a weight of mg. Now this angle here is 30, so that angle is 30 degrees. That's 30. I'm not done with my forces yet though. What else have I got to put on here? Normal contact force. I'm going to call it R between the particle and the plane. What else am I going to have? Friction. Now, A is on the point of moving in which direction?
Down.
Down the plane. So which direction is friction going to be?
Up.
Good.
See, I was right, just the wrong question.
That's the story of your life. There we go. That was maybe a tiny bit harsh. Right. So that's particle A. Brilliant. Good start. I'm going to do a similar diagram for particle B before I start doing anything in particular. So particle B is over here. What forces are there acting on particle B?
Tension.
Weight and tension. So we'll put those in. So there's the tension. It's the same tension because it's a light inextensible string over a smooth pulley. So the tension is the same in both portions. And it had a mass of lambda m. Lambda m. So that's lambda mg. This is particle B. Okay. We're told that it's on the point of moving. It's not moving. It's on the point of moving. So these particles are in equilibrium as we start out. So in part 1, section A, lambda is a quarter. And the acceleration in the system is 0. Both particles are in equilibrium. Now it's just a case of writing down some equations. So I'm going to do that. If I look at particle B and I resolve vertically, then actually something happens straight away, doesn't it? If I resolve vertically, I've got that the tension minus a quarter mg is equal to 0. In other words, I have found the tension in my string instantly. T equals a quarter mg. That feels like a good start. It also feels like I've exhausted what I can do with particle B at this stage. So now let's focus our attention on particle A. Let's start by resolving in the direction where there's not so much going on. So if I resolve perpendicular to the plane, I'm going to take that direction as being positive, but remember there's no acceleration, so I equally could take the other one. Then R minus, now we are thinking we can do this, what is the component of this force in that direction? That is mg something 30, cos. Because it's adjacent to the angle that we've marked. So that is mg cos 30, and the resultant of that, oh, hang on, yes, and the resultant of that is 0. So we've also got that R equals mg cos 30. Cos 30 is root 3 over 2. So R is root 3 over 2 mg. Ace. There's only one direction left for us to deal with. Parallel to the plane, and let's take up the plane as being the positive direction, although again it doesn't matter. We have up the plane we have tension and friction, and down the plane we have, well, if that was If that one was cos, the other one must be sine. That's the opposite part of that. So this is mg sine 30. And that's equal to 0 as well because it's not accelerating. There's no resultant force, it's in equilibrium. Brilliant. We know what t is. Sine 30 is a half. So we've got that. So I think we've got that f is, what would that be? A half mg, take away a quarter mg, so a quarter mg. Oh, it's going well. We're supposed to be finding mu. It's on the point of moving. And the fact that it's on the point of moving tells us that the friction is equal to mu r. The friction we found to be 1/4 mg. R we found to be √3/2 mg. That times mu. Mg cancels out. It leaves us doing 1/4 divided by √3/2, which is, what is that? 1/2√3. So if we multiply by √3/3, it's √3/6. Or you could use your calculator to rationalise the denominator for that. There we go. Do you see how we were just very, very logical? We just did our different directions, got our equations, sorted out our equations, put it together. That was it. Now, show that the value of lambda must be less than a half. Okay, well, if we go back a step, let's think where we've used lambda. So we used lambda in finding out the value of t. T was lambda times mg. So if we think of this for part B, t is lambda times mg. That then gave us, when we looked at the parallel to the plane equation, we had that lambda mg plus f minus, now at the mg sine theta, that didn't rely on it at all, did it? Nope. So minus a half mg was equal to 0 at that point. Now, in order for this to be on the point of moving down the plane, that frictional force would have to be greater than 0. So that force there that I put, so F would have to be greater than 0. And we've just got that F is a half mg minus lambda mg. So if F is greater than 0, that implies that half mg minus lambda mg has to be greater than 0. And if I rearrange that, mg cancels out all the way through. So lambda has to be less than a half. And that's the condition that I have for it being on the point of moving up the plane. Lambda has to be less than a half. Now remember, lambda is the ratio. Lambda is the ratio of the mass, isn't it? It's what you're multiplying the mass of A by to get the mass of B. And it has to be less than a half for it to move down the plane. That means if it's bigger than a half, then it's going to move in the other direction, isn't it? Okay? So for what we've had to happen, lambda has to be less than a half. Things change. So in part 2, lambda is now equal to 2. Now notice that means that lambda is greater than a half. So now it's moving in the other direction. So it's now moving up the plane. And that's quite an important thing to notice in this. The kind of link with what you've just done in the previous part to what you're doing next. And the acceleration is 1/4 g. So that acceleration is an acceleration up the plane. So B is going to move down. We now need to find the exact value of mu. So I need to think about some of these things again. If I go back to what I did before, I'm now saying, what do I need? If I think about, do I need a new diagram or can I just go for it? Are you happy? I'm going to draw a new diagram just so we know what's going on. So here's particle A. A few things have changed. We've still got a reaction. We've still got a tension. We've now got, we've still got the weight, which was mg at an angle of 30. But now we've got the frictional force opposing the motion up the plane. So we've now got F in that direction. That's particle A. If I think about particle B, I've still got the tension, and I've still got, well, I've now got 2 mg as being its mass. This one is accelerating in that direction with a quarter g, and this one is accelerating downwards with an acceleration of a quarter g. So if I start to work through the process again with this, if I think of particle B, I'm going to resolve downwards. 2mg minus t is the mass times the acceleration. So I've now, if I rearrange this, I've got that t equals, what's that going to be? 2mg, take away a half mg, so that's 1.5 mg. Have I done that right? Yes, I'm sure I have. Everybody happy with that? So that's the tension now. Would the reaction have changed in what we've just done? No, we've not changed anything about the vertical thing. So if we think about A and we think about perpendicular to the plane, we've still got the same situation. We've still got that R is mg cos 30. So that's root 3 over 2 mg. But that's the same. I'm writing it just for completeness there. Now if we think about A going up the plane, looking at my force diagram, I've got T minus F minus mg sine 30. So same deal as before, although we've got F in the other direction, is the mass times the acceleration, which we now know to be 1/4 of g. So let's put things together here. This is root 3 over 2 mg minus F minus a half mg is 1/4 mg. So F, I think, is root 3.
T is just 3 over 2, not root.
Oh, it's just 3 over 2, thank you, yeah. T was just 3 over 2. Good spot. Oh, that's nicer anyway, isn't it? So root 3 over 2 mg, take away half mg is mg. Take away a quarter, so that's 3/4 of mg is our value of F. And using F equals mu r, we now have that 3/4 of mg is mu times root 3 over 2 mg. So we found mu again. This time as being 3/4 divided by root 3 over 2. Which is 3 over 2 root 3. And if I multiply top and bottom by root 3, that is root 3 over 2. And we got there. Again, it's all about structure. It's all about going step by step, resolving in your directions, seeing what you get, and putting it together, working very, very logically. Don't try and do too much at once or skip steps. And that is maths.